is from the CPU, what happens inside the CPU, from a single core all the way to multi-cores. You have seen how pipelines work. You have seen how caches work. Professor Govindarajan also talked about how main memory works, right? So essentially now if you want to have a more holistic view of the system, the one thing that's essentially remaining is the secondary storage or the storage subsystem, or secondary memory or the storage subsystem, right? So what we'll discuss in this lecture is essentially a couple of things, right? We'll see how disks work, we'll see how SSDs work, and what are some of the few things that you can do to sort of make them more efficient and more performant, for example, right? So first things first, why do storage systems at all? I mean, we have gone all the way to memory. Why touch upon storage systems? I'm actually looking for answers. Last level of memory hierarchy, all right. That's true, but still doesn't really answer my question. Sorry? Cheap and large storage, okay. That's also, okay. All these are known facts, right? I mean, it's cheap and large, it's non-volatile, it's the last level of the memory hierarchy, everything's known. But why is it that you essentially need to study storage, or you need to study disks and SSDs as a part of computer systems design? What is the eventual purpose that these things actually solve? So think about the life cycle of a program, right? Whatever it is that you run on a machine, where does it actually originate? Or what does it originate from is the real question. Again, I'm actually looking for answers. A program, a binary, Microsoft Word, Mozilla Firefox, where does all of this actually start? The storage, right? I mean, when you double click on your Word, or you say ./a.out in your shell script, essentially you refer to a binary, which for the most part is sitting somewhere on storage, right? So in the life cycle of program, you get that binary out from storage, you lay that out in memory, and then all the magic that we have talked about so far actually happens, right? So instructions are fetched, they are executed, stuff stored back into memory, and probably eventually written to disk, right? So if you are working with programs that are working with large sets of data, they can't fit into memory. I mean, they definitely can't fit into caches, or starting with the registers. Can't fit in registers, can't fit in caches, can't fit in memory. So eventually they have to be stored somewhere on the last level, the big, the not so fast level of storage. And eventually, if you don't optimize this particular aspect of computer system design, then your program, your quote unquote big data, or your machine learning program, whatever that might be, can eventually be bottlenecked by this particular subsystem, right? So essentially the idea is, because it can potentially be on the critical part of your program execution, it is sort of important to study this as well, right? Any questions so far? I mean, this time around, I'll make sure that I go beyond half of my slides. So, all right. So I was trying to just make a case for why is it important to sort of study storage systems, right? So there are two of these figures over here. One of them I've sort of borrowed from one of the research papers from Georgia Tech, and it shows you the disparity in terms of latencies between different levels in the memory hierarchy, right? So that's one way of visualizing this. So you have, if you look at in the power of 2s and cycle access latencies, the SRAM caches are very fast. The hard drive is super slow, but again, it's large and it stores a lot of stuff, right? Again, a different way of visualizing the same thing is that the memory hierarchy starts at the register file, goes all the way to the hard disk drive, right? So eventually, all your data or all your execution is going to happen on the data that's sitting in the register file, and that data eventually has to get there. And if it has to be brought from the lowest level of your memory hierarchy, which is essentially your SSD or HDD, then your performance of a program is actually determined by last of these two levels. Yes?
Yes, actually we are moving towards nowadays emerging technologies like VRAMs and all.
Sure.
Suppose like we got a fast switching in terms of get something in terms of nanosecond. So the hierarchy with that.
Okay, so you figure out a new memory technology which has a switching time of few nanoseconds.
Yeah, and it's not volatile.
It's non-volatile. All right. So I think some of that actually covers this, right? So here, if you look at this figure, you have that PCM or phase change memory that's sitting very close to DRAM in terms of access latencies, right? So you are right. If you find out some memory technology that has access latencies as close to that of, let's say, DRAM or similar-ish, then you can put that anywhere in the hierarchy, right? I mean, you could put that in lieu of DRAM or in addition to DRAM at that level where your main memory sits, or you could also make the last level, which is your SSD or your HDDs faster by using that technology, right? But we'll see there are certain more sort of things that need to be considered while just willy-nilly replacing whatever you have at the level of the storage with something fancy. There are more things in terms of software that we'll consider. We'll just take a look at. Okay, good point. All right, so now that we have motivated as to why we need to sort of study storage, let's look at a few trends. And again, this is sort of trying, or me trying to convince you that this is, or storage devices are also a very important part of system design, right? So these two graphs over here sort of show some amount of projections in terms of the amount of data that is being generated by different devices, or the data that's being collected and how that's projected to increase over time. So the x-axis over here is the years. So it starts at 2010 and I think ends at around 2025. And then you can see the amount of data that's going to sort of be generated is going to be exponential in zettabytes, right? Anybody know how many zeros there are in zettabytes? How many zeros, how many parts of 10 in 1 zettabyte? All right, I don't know either. So anyways, sorry? Huh? 18? Zetta, okay. Okay, 18. So 10 to the power 18 bytes is 1 zettabyte, right? And that is exponential in terms of zettabytes. The other thing that it shows here is the kind of data that's being generated. So you have data that's being generated from embedded devices, entertainment, which is essentially your high definition videos and things like that. So the point here is that the amount of data that is being generated is going to increase exponentially. All the data is going to be stored on storage devices, and hence essentially most of your programs sometime in the future are going to be bottlenecked by your storage device, right? So again, the one thing that is also to note here is how the density of storage, right? How many bits per square inch or per square millimeter that you can store is not increasing that fast, right? So this is a little older graph that shows on the x-axis, again, this is time progression. So this is 1960s all the way to 2010s. And on the y-axis is a log scale depicting how the storage density of hard disk drives has been increasing over time, right? So if you look at this, from the 60s, it went on really quickly, and then it's been making some progress, but it's sort of not keeping up with this exponential growth in terms of data generation that has been happening, right? So again, one more motivation for studying storage systems. Again, this kind of shows you the disparity in terms of access latencies, right? So, and how things have changed over time with respect to how access latencies of DRAM have changed versus how access latencies of storage have changed. So again, this is access time in nanoseconds. This is also on the y-axis is cost per gigabytes. Oh, sorry, this is sort of cost per gigabyte, right? So as if you go from 1980 all the way to 2005, disks have become really, really cheap, right? And that's why you can buy a terabyte disk for like 5,000 rupees these days, or maybe even less. All right. Okay. Any questions so far? No? Okay. So what we have seen up until now, as I mentioned before, was in this summer school, we have covered these points. We have covered what happens within the CPU, and up until the point where the data sits in DRAM, and that's where we kind of stopped. So what we're going to look at today is the rest of the system, right? So the rest of the system is connected to what we had seen before by various things that are essentially known as interfaces, right? So you have the CPU that is essentially connected to this sort of an ASIC over there, which essentially is known as the I/O bridge, right? The I/O bridge has a whole bunch of buses that are hanging off of it, to which all your different storage kind of devices actually do connect to, right? So you have your HDDs that are connected to this I/O bridge through various interfaces, right? So what you can think of, these are essentially just buses, and then these buses follow different kinds of protocols, and that defines what kind of an interface that that particular I/O device is going to use to connect to the system, right? So you can have an interface which is serial ATA or SAS. These days, you have a new set of I/O devices that are connected probably directly to the CPU using something known as the Peripheral Component Interconnect Express, so PCIe Express. So the PCIe Express's root node sort of sits here on the CPU. So if you have the newest generation SSD, rather than connecting through the I/O bridge and getting your memory or I/O requests through here, you would have an SSD that's connected directly to the CPU using PCIe, right? So this is essentially just to give you a flavor of how things actually are connected in the system and how sort of information flows from one level to the next one. Now what we're going to do is essentially try and look at this thing in a slightly different way, right? So what I showed before was how things are connected in a sort of a cartoonish fashion. But if you want to really sort of show that in a block diagram, you have your processor and your caches and everything with the DRAM sitting over here. Then you have multiple sort of disk controllers sitting over here, and you have a whole bunch of I/O devices that are hanging off of it, right? And again, if you open up a computer system, you can actually take a look at how things are differently connected, right? So this is where your CPUs goes, this is where your DRAM DIMMs go, and everything else, which is essentially a block over here, can potentially be mapped to a block on the motherboard over here as well, right? All right. Okay. So first things first, how are storage devices actually different from the memory devices that we have seen so far? So when it comes to memory, the access interface is a load store interface, right? So anytime you want to access a piece of data, you either do a load, which essentially goes through the memory hierarchy, gets you the data into the register file or the cache or wherever it is that you want to be. Similarly, you have to push the data back into memory, you do a store, and the data sort of is stored into memory. In the case of storage devices, things change a little bit. The access granularity is a little bigger. So what is the minimum access granularity in terms of when you're doing the load store interface? What was the minimum access granularity that you can do over there? Let's say going from the processor pipeline to the caches. Sorry? Say that again? 4 to 8 kilobytes? Is that seems a little too big. It's probably a little smaller than that. 64 bytes, or even smaller than that, right? So if you are making a cache access request from the last level cache to the memory, that access granularity is at the size of your cache line size of the last level cache, right? If you are making a request from your processor pipeline to your caches, what you actually need is a register worth of information, right? So that is essentially determined by how or what is the bit size of your ISA. Is it 32-bit? Is it 64-bit? And that's the granularity at which information is exchanged between the processor pipeline and the caches, right? But when you're talking storage devices, you tend to do a much higher access granularity sizes, which is essentially 512 bytes at least, if not bigger. So any reason why you think access granularities are bigger here as compared to processors where these are much smaller? Access time is more, right? And what does that actually entail? So access time is more, and then what is it that you're trying to hide by doing larger granularity accesses? Is there a benefit there? Sorry? Right. And that is a function of what in the program? Is there something in the program that you can exploit which helps you sort of hide those latencies? Locality, right? So essentially, that's the whole idea. because the storage devices are relatively slow. We saw, hard drives are at the bottom of the pyramid and costs you millisecond to access them. Once you have to go to the hard drive, you want to make sure that you get, hopefully, all the data that you really need, right? So that's why you go down there. The access granularities are at least 512 bytes, if not more. Typically, they are in the order of 4 to 8 kilobytes, right? And essentially, does this remind you of anything else, this sizes? Sorry? Page size, right? So you would see how these things connect throughout the system. A 4 kilobyte is the DRAM page frame size as well that Arka was talking about before, right? All right. Accessing the storage devices is through a much deeper software stack. So, I mean, the load store interface, you just go over the hardware and all the way to memory and you get the data back. But if you have to access the storage devices, you can't just do that. I mean, it has to go through the operating system, and the operating system has to traverse a software stack before it can actually get you the data, right? We talked about much higher latencies. We talked a little bit about how interfaces are different, right? So you can have a hard disk drive that's connected to the system via interface 1, which is essentially SATA, and we don't really need to go into the details of what these interfaces do. You just sort of, they have different capabilities, and they can connect different kinds of devices to the system using that, right? So again, the one thing that is important over here is essentially trying and figuring out what are the metrics that we use for comparing different kinds of devices, right? So some metrics don't change at all. I mean, latency always is sort of like the primary metric when you're talking about performance. One thing that we haven't talked about much over here is essentially the I/O bandwidth, right? And in the I/O world, the one most important metric is essentially what is known as IOPS, or input-output operations per second, right? So essentially, the number of operations, which are again at the granularity of what size again? So what would be the access granularity size? We just talked about that. Well, in this case, it's going to be at least 512 bytes, right? Typically 4 kilobytes. So how many 4 kilobyte operations from this I/O device that you can do actually determines how many input-output operations you can do per second, right? So the bandwidth here again is a function of the minimum access size, which is typically like 512 bytes or 4 kilobytes. All right, so having sort of introduced most of the things over here, let's take a look at what sort of workloads kind of look like in the I/O world, right? So when you look at any kind of a device spec sheet, what the rated performance would be given out as is in terms of different kinds of workloads, right? So you would see all these terms being thrown around, which is essentially random and sequential, and a device's performance is sort of rated as a function of how does it perform on a random workload or on a sequential workload. So let's try and define what exactly are these workload types and what do they really mean, right? Okay, so a random workload is essentially random, right? So if you are making accesses to a storage device for these different blocks, which are essentially 4 kilobytes, if you are doing them all over the place, right, then it's sort of like a random workload. And in this particular example, you can see if you type this sentence over here, and if you follow your keystrokes on the keypad, then it would sort of seem like a random pressing of keys, right? But if I was to talk about sequential workloads, if I was to just start typing in numbers from 1 to sort of 9, then it would be pressing one thing after the other, and that is essentially what sequential workload is kind of defined as, right? So a good example of a sequential workload is something like this, a CD-ROM, right? So on a CD-ROM that stores a movie, for example, right? So you start at the start of the movie, and then you watch all the frames all the way to the end, and that's when the movie stops, right? So you are always going to watch frame 1 after frame 0, frame 2 after frame 1, so on and so forth, right? So it's a very well-defined sequential access pattern. And essentially, the reason why I'm mentioning these is if you understand the workloads and how the workloads behave, you sort of get a feel of what type of a device is better in what type of a situation, right? So I mean, if you understand what kind of access patterns my device is going to make, I can figure out which kind of a device is going to be better for my particular case as well, right? Okay, so all right. So we've defined what random and sequential sort of looks like, but in the real world, nothing is completely random, or no workload is completely random, no workload is completely sequential. So all workloads that exist have some function of randomness, have some function of sequentiality, right? So again, a particular workload that you look at, for example, a database application, right? If you go down all the way to the storage level, it would have certain access patterns where you access block 0 after block 1, or sorry, block 1 after block 0, block 2 after block 1, so on and so forth. But in certain cases, you would access block 1, block 50, block 21, things like that, right? So it's a mix of both of these things. Not only that, most of the workloads also have varying request sizes, right? So when I said before that the minimum access granularity is 512 bytes, that's what it is. It's a minimum access granularity, right? But a particular workload can demand more data. So it would say, well, okay, I don't need just 512 kilobytes, I need 256 kilobytes, right? So in that case, your workload also has a distribution in terms of sizes as to what kind of request size it wants. So in this particular graph, on the x-axis, you have different request sizes, right? So it starts at 4 kilobytes, and I think it goes all the way to 52 kilobytes, if I'm not mistaken, right? And then it shows for all the requests that were 4 kilobytes, how many of them were reads and how many of them were writes. So it gives you a feel of that the request sizes or request access sizes are also sort of distributed all over the place. It starts at minimum access granularity, which is 4 kilobytes, and is distributed over, not only over space, but also over time, right? So you could have potentially a program phase where you're just doing random, or you're just doing sequential. You could have a program phase where you're doing both random and sequential, right? So, okay. So now that we have that, let's take a look at how sort of this fits into how devices are actually structured, right? So we talked about what kind of workloads we have, and now we're going to look at the internals of devices and how do these kind of workloads fit into the different kinds of devices that we're going to talk about. All right. So anybody ever open up a hard disk drive, see what the internals are, right? All right, 2, 3, 4, wow. Not bad. Okay, so when you look at a hard disk drive, it has sort of multiple components. So a hard disk drive has something which is known as mechanical moving part, and that's one of the reasons why these hard drives are very slow. And bear with me while I sort of explain this a little bit. So you have all these different platters, right? These are round, shiny objects with magnetic coating on top, right? And these platters, there are multiple of these platters that are stacked on top of each other. So you can think of that as a pancake stack, for example, right? And then these platters are connected to this central spindle over here, and this spindle can spin at very high velocities, right? So when you look at a specification for a particular hard disk drive and it says 7200 RPM or 15,000 RPM, what that essentially means is how fast this stack of data essentially is actually moving, right? Now, the next thing that you need to look at is this sort of the mechanical moving arm over here. At the end of it is this read-write head, right? So what happens in this particular case is that you have all these spindles that are spinning at very high velocities. This arm can actually move around, right? So it can cover the entire sort of radial of this particular stack. So so in order to access a piece of data, you can think about that this particular mechanical moving part, right? This actuator arm has to go to the point where your data is actually stored, right? So that brings me to the point as to how the data is actually stored. So let me just quickly go over to the next slide, right over here. So if I was to represent this as a cartoon, now you have all of these spindles that are sitting on top of each other. Now, data is stored on these spindles in these concentric circles over here that are actually known as tracks, right? Now, each one of these tracks is actually divided into sectors. So if you see this small black part over here on a track, this is actually a sector. And can anybody guess what the size of this sector is going to be? Sorry? 512. Why is that? It's one read write, exactly, right? So the size of this sector is essentially your minimum access granularity. If the minimum access granularity of your device is 512 bytes, then this sector is going to have a 512 byte size. If it's more than that, it's going to have a larger size, right? Anyways, so in order to access a particular file on this disk, what you essentially have to do is figure out what is this start track and start sector from where your file actually starts, right? So then the motor inside the hard disk drive is given this particular command that, okay, this is where this particular file starts. So you should just move over to that track and that sector, right? It moves over to that track and that sector, or well, it moves over to that track and it waits for that sector to sort of spin underneath it, because remember, these things are actually moving, right? So it waits for this sector to come underneath it. Now, this actuator arm at the end of it has that read-write head, right? So as soon as that sector comes under that head, it reads that information, right? So there are 2 or 3 different kinds of latencies involved in reading a piece of data. First, you have to figure out where the track is. You have to go to that track. Then you have to wait for that particular sector to come underneath the read-write head. And when it does that is when you start reading the data, right? So there are these different sort of latencies involved. Now, that is essentially what makes these hard disk drives slow as well. Now, this is essentially a very bad robot, if you can think of it that way, right? So anytime you have to access data, you have to move this arm to the right place, and that takes up a lot of time. Remember, when we are talking in terms of CPU cycles, we are doing nanosecond latencies. Now, however fast you can move this arm, it cannot match those nanosecond latencies, right? I mean, it has to be sort of milliseconds at best. And that's where this high access latencies of this hard disk drives comes from, right? So that's essentially what I'm talking about in this particular slide where, in this slide, the next one, where you have these different times that are sort of broken down for a particular access of the hard disk drive. So you have this seek time, which is essentially going to the right sector. Then you have the rotational latency or going to the right track. So seek time is going to the right track. The rotational or rotational latency is waiting for the right sector to come underneath the read-write head. And the transfer time is essentially how much time it takes for you to read out that sector, right? Now, having this background information, right? Now let's try and connect it to what we learned about the workloads. So let's say for the time being, we have only 2 types of workloads, which is essentially a completely random workload and a completely sequential workload, right? Now, and let's forget that there is any gray part in the middle. Which one of these 2 do you think would work better on a hard disk drive that works this way? Sequential, okay, why is that? Okay, that's correct, right? So essentially, there is also a catch there, though, right? Well, okay, for the time being, let's forget about that. But you're right, right? So if your data is stored such that the data that you have to access is, let's say, in track 0, sector 10, sector 11, sector 12, sector 13, that way, you just have to move over the actuator arm once, and then you can just start reading the data, right? So in that case, your latency is, the overall latency for access to your data is actually reduced, mostly because of what kind of locality? Spatial, right? So you have spatial locality here, and your access latency is actually reduced, right? So, all right. And then there are various other latencies involved as well, right? So I mean, the controller has to be given the command that, okay, move over there, and that takes a non-zero amount of time, and that sort of adds up to the entire latency of a disk access as well, all right? Okay, so I'll quickly go over what is sort of the state of the art in hard disk drives today. So when we looked at how data is stored, we said, well, okay, there are these concentric circles or tracks that store data, right? But the problem that has happened over time, or the challenges that people have had over time, is essentially how do you increase the storage density of these storage devices, right? So essentially, if you look at how regular sort of hard disk drives or traditionally hard disk drives have looked like, you have this track, right? So this is just a part of that concentric circles that I was talking about. Then you have this head, which essentially consists of a write part and consists of a read part as well. Your data is actually stored in this blue area over here, or over the track. Now, this green area over here is just sort of, you can think of it as a guard band, right? I mean, because you have these concentric tracks, so you have to have some differences between the two concentric tracks so that you don't have destructive interference between the data that you're storing on these tracks, right? But that essentially means that this all space, which is all magnetic space that can actually store data, is being wasted, right? So how do you go about sort of using that space to store useful data? And that's where people came up with what is known as shingled magnetic recording, is essentially figuring out a way to store data such that you can sort of also store data over this guard band that you had before, right? So this is one mechanism of increasing your overall storage density, but again, it comes with its own set of challenges that we're sort of not going to get into right now. And its name comes from this shingled or roof shingles that are pretty common out there in the Western world. All right? Okay. So having done disks, and I think this is the point where I move on to SSDs, right? But before that, any questions on hard drives? Yes? Sure. All right. So there are two moving things here, right? So the disks are actually spinning, and the arm is the only moving thing, right? So the disk is spinning, right? As soon as you turn on the drive, it's spinning. The moving part, the actual moving part, is just the arm. So a lot of the times when your drive is corrupted, all that means is that your arm just ran into the magnetic platter, right? So but the actual moving thing is just the arm.
And the arm also moves from the center to the circumference for each.
Exactly. Yeah. Yeah. Yes.
How the heat dissipation is calculated?
Okay.
These are magnetic drives.
Right.
Dissipate some heat.
Right.
How are these being figured out? Is it the rotations per minute in the factor causing heat, or what is the actual cause of heat?
So I mean, there is some logic over there for giving commands to move the motor, right? It's also a function of what your workload is doing. So if your workload is making that arm move back and forth a whole lot, then essentially there is a lot of heat generated as well, right? The disks are themselves spinning at 15,000 RPM per minute. So just keep them spinning also generates some amount of heat. So there are 3 or 4 different things that generate heat, and to the best of my knowledge, I'm not sure if it is that big an issue, right? The heat dissipation is not as big an issue in hard disk drives as it is in, say, for example, CPUs, right? Because there's a lot of switching happening in CPUs than there is happening in hard disk drives. Make sense? All right. Yes. Sure. That's a good question, right? So why don't you have more read-write heads? So in this case, let me just go back to, so in this case, you have one read-write head per disk platter, right? Why can't you have multiple read-write heads per disk platter? I agree. I mean, it's a decent idea, right? Why don't you do it? Sorry? That's one thing. They might hit each other, right? Because the one thing that you have to consider here is that the distance between the read-write head and the spinning platter is actually in microns, right? So there is a very thin layer of air that's there between the read-write head and the platter. So it's a very delicate ecosystem. You can potentially put in there, and that could potentially be a decent idea, but it could also be pretty dangerous, right? So you don't want to maximize the number of components that can actually fail, right? All right, yes. Sorry? Right. So it's a function of your workload, right? So if so let's say I have 10,000 different files on my machine and I'm just randomly accessing each one of them. So it's me who's causing the trouble, not the device itself, right? So if I could magically convert all those accesses that were potentially random into sequential accesses, my device would do really, really well over there. That's also not necessarily true, right? It's also a function of how the device actually stores the data. That's a very good point, right? So just because it's one file doesn't necessarily mean that it's going to be a sequential access. It could potentially be stored all over the place.
So in the next slide,
Huh.
you show the drawbacks.
Huh.
So in the track 1 is guarded by drawbacks on both the sides. And
Okay.
track n+1 that is completely
Right, so this one's not written to yet, right? So this one is something that has already been written to, so there is data over here. So the blue part is data. This track is something that would be written sometime in the future, right? Yes?
What is the cause of a hardware corruption?
So one of the causes is essentially your read-write head just crashes into the device platter, right? So that's one part of it. There could potentially be other causes as well. I mean, most of the time, it's some sort of mechanical failure, right? I mean, it's usually not electronic. It's some mechanical thing that has failed on the drive, right? If the arm crashes or the motor breaks down or something of that sort, usually that's the cause. Any other questions? That's a good question. Sometimes it is, right? I mean, again, as I said, it's a very delicate ecosystem. So essentially, what you'd have to do potentially, you can't use that head, right? I mean, that head is gone. What you have to do is essentially open up the drive, get out the platters, put them somewhere else where they potentially can be read again, right? So essentially, just constructing a new hard disk drive from spare parts, essentially, which is essentially your old hard disk drive. So the data is there, right? The data hasn't gone anywhere. It just can't be read by this particular arm anymore, or the read-write head. Make sense? Right. So it can be reconstructed. Huh?
The latency that you see with the ARM reading,
Sorry?
the latency that you see with the ARM reading
Sure.
is like pretty perceptible, palpable amount of latency. So are you saying that all of that is shielded by the cache structure?
So what I'm not going to talk about is this multiple levels of caching that happens, right? So we are just looking at devices right now. And there's a whole lot of caching that happens in the hardware and as well as in the software. So we'll take a look at that if I can get to that, right? So, all right. So let me sort of quickly go over some parts in, okay. All right. So now we sort of going to move on to the next thing in storage devices, which are SSDs. Anybody know what the full form is? Solid state devices. All right. So you only started seeing them to be around on the market in the last 5-7 years, right? Or being affordable in the market in the last 5-7 years. They have been around since the 1980s. So NAND Flash, which forms the basis of the solid state devices today, which is essentially the storage technology, the underlying storage technology, has been around since the 1980s. Why is it that you only see solid state drives today? Why not before? The technology has been around for 40 years. That's one part of it. So technology scaling has allowed higher capacities. What else? That's a good point, actually. More demand by high CPU speed. Okay. So you need faster access to storage. All right. Okay. What else? Sorry? Less moving parts, so lesser chances of failure. All right. Anybody can think of anything that's non-technical. Exactly. Very good point. So this has what has happened, right? Over time, if you track how much it costs per gigabyte. And again, this is a slide that I have borrowed from over time. Just only very recently, if you look at 2009, is when it has gotten super economic, right? To manufacture an SSD and sell it at a price where you and I can actually buy it, right? I mean, if it was $40 per gigabyte in 2007, I mean, why would you really buy it if you can buy a terabyte hard drive for, whatever, almost nothing? Right? So that's one of the things that is essentially completely non-technical. It's dominated by market economy. And I mean, of course, there was a demand for better storage devices because the workloads were behaving that way. So people found a way to make it more economical. But essentially, the underlying reason was that the market made it possible for economies of scale. You could sell and manufacture SSDs at low costs and make it affordable, right? All right. So yes.
Still, why SSDs costs means even a 1 TB SSD costs something equivalent to a normal level CPU, normal level laptop, I guess. The last time I checked the price, it was still at around 25 to 30,000 1 TB SSD.
Right. So I mean, again, the costs have not really caught up, right? So again, if I look at over here, right? So the costs have sort of caught up, but not exactly. So that's one part of it. There is, so this is just for flash, right? This is just the component which actually stores the data. There is more that goes into an SSD than just flash. So there is underlying electronics, there is packaging, other costs involved as well, right? And plus, because there is not a whole lot of SSD sort of sales happening, the margin that is there per component is also higher. So there could be multiple components to that as well, right? So all right, so let's take a quick look at what the underlying storage technology in SSDs is, how that works, and what are the different design considerations that you have to take care of while designing SSDs, right? So the underlying storage technology in SSDs is what is known as NAND Flash, right? One thing that you have to sort of keep in mind about NAND Flash, and that will sort of percolate through this entire discussion over here, that changing a 1 to a 0 is relatively easy over there, right? But changing a 0 to a 1, or to set back zeros to a 1, you have to write to an entire group of flash devices, right? So if I have, in this case, 4 flash devices, if I want to change a 1 to a 0, I could easily do that. But if I have to change a, if I have to go the reverse way, then I have to write or reset this entire set of flash devices that are connected in sort of series over here, right? So that is essentially one underlying assumption about the NAND flash technology that will sort of percolate through our entire discussion that we'll have in the next set of slides. Okay, so all right. Okay, so when we talk about SSDs, right? SSDs are essentially nothing but a collection of these flash devices. Now, the minimum granularity at which you can access these SSDs is what is essentially known as a page, right? Sounds familiar, right? This page terminology would carry you from the memory systems all the way to storage systems as well, right? And even the granularity sort of remains somewhat consistent. So a page here is 4 to 16 kilobytes depending on what you're looking at, and as times change, these numbers change as well. Now, a collection of these pages is organized into what is known as a block, right? So a block can be anywhere from 128 KB all the way to 8 megabytes, right? So there are a lot many pages in a particular block. The one thing that you have to note here is, or if you look at literature, a block could also be called an erase block, right? So one of the peculiarities which arise because of what we talked about in the last slide is the fact that you can write to a page individually, right? But you have to erase a block at a time, right? Okay, so you could potentially have multiple pages in a 128 kilobyte block. You could write to those pages individually, but if you were to sort of clean the page out, you would have to sort of clean the entire block at a time. And just bear with me, and we'll talk a little bit more about that, right? So now that your SSD has been divided into this collection of pages, right? So if you have let's say a terabyte SSD and each page is 4 kilobytes, then you have a collection of these pages that are available to you. How do you figure out where your data is actually stored? So Arka talked about virtual memory, right? How do you do it over there? We translate it, right? So another level of indirection. You have a virtual address, you translate that into a physical address. Similarly, the exact same concept applies to storage devices as well, or SSDs particularly, right? So you have this collection of pages that form your SSD, and you want to have some sort of a mapping that tells you these are the set of pages that are actually holding the data that I want, right? So if you have a file that is so many kilobytes big, there would be a mapping stored on the SSD itself, which will tell you, okay, these are the pages that you have to read to actually get your file, right? Okay, so that's the first basic part of it. The next thing that or some of the terminology that we're going to look at is, so this figure is a different representation of what we have just talked about, right? And you can somewhat draw parallels between this organization and what we had seen in sort of DRAM before, right? So if you look inside or if you look at an SSD, you would see a whole bunch of these chips, right? Similar to what we saw in DRAM. If you look at a DIMM, you have a whole bunch of these chips, right? Inside each one of these chips, you have a whole bunch of planes, right? And inside each one of these planes is essentially a whole bunch of blocks. And inside each one of these blocks is pages, right? So again, if you look from a top-down perspective, right, looking from an SSD inside or outside an SSD on the inside, you would see chips, then planes, then blocks, and then pages. All right? The way you store information is each one of these cells, the big blue things that we saw a couple of slides before, could either store 1 bit or multiple bit, right? So if it stores 1 bit, then it's called a single level cell. If it stores 2 bits, it's called a multi-level cell. If it stores 3 bits, it's called a triple level cell or a TLC, right? Okay. The next thing that we're going to talk about is essentially arising because of the NAND Flash drawbacks that we had seen before, right? So when you are reading from the device, you can read an entire page, right? So you read an entire page or a collection of such pages. If your page is in what is known as an erased state, right? So it has to be in an erased state before it can actually be written to. You can write into that particular page as well, right? So if you have 4 kilobytes worth of data and I have a page that is in an erased state, I can just drop that data onto the erased page. What I cannot do, however, is essentially do in-place updates, right? So if I have a page that's sitting in my NAND Flash device, a 4 kilobyte piece of information, which is essentially, let's say, a piece of my file, right? And I change some piece of data over there. So on a typical hard disk drive, what you would do is, or in the cache hierarchy, right? You would just go in, figure out where that data is, and flip those bits if they needed flipping, right? In this case, you can't really do that, right? What you essentially have to do is, if I flip 2 bits in a 4 kilobyte page, I read that entire page from where it was, flip those 2 bits, and then I have to write it to a new location, right? And I mark that earlier page as invalid, okay? So to change a single byte or even a single bit, you read the entire page, change it, write it somewhere else, right? Okay. All right, so and this is what I talked about here as well, right? So you can't do in-place updates. Pages cannot actually be overwritten, right? So you have to do this sort of indirect writes that are over there. Now, we talked about invalidating pages, right? So I have updated this piece of information. I read that piece of data, from where it was sitting. I modified the information, wrote it somewhere else. This page essentially has now been marked invalid now, right? So, but at some point, this can actually contain valid information at some point in time, right? But not right now, not until this page has actually been erased, right? So what we talked about before was, if you want to write information into a page, it has to be in an erased state, right? And erasures can only happen at block granularities. So that's essentially what we're talking about over here. So if you have a 256 kilobyte block that has a whole bunch of 4 kilobyte pages, until and unless each one of these pages that are sitting within that block has been marked invalid, you can't actually erase that entire block, because block or erasures happen at block granularities, and make that space free for new incoming data. Did that make sense at all? So I have this big page, right? Or a big block that has a whole bunch of pages. Some of them have valid data, some of them have invalid data. The ones that have invalid data, I can't actually write to, right? Because there are no in-place updates. I first have to erase those pages, and then can I only write to them. But I can only erase at a block granularity, right? So what happens to those pages that actually have valid information within this block? Did that make sense? What would you do? Okay. Okay. That's a good point. Have you sort of seen this sort of a thing somewhere else? So again, let me sort of recount the scenario. Big block, some invalid pages, some valid pages, right? Now, let's say I have 8 pages in my entire block. 6 of them are invalid, 2 of them are valid. I cannot write to my invalid pages, right? Because I need to erase the block first. What do I do? Okay, right. So what you're trying to do is sort of reclaim space, right? So you have, out of these 8, 6 are bogus, 2 actually have valid data. So I take the information out of the 2, copy it somewhere else, so I can, at the end of it, get 8 free pages to write into. This sort of functionality, have you ever seen before? Think about or even to give you a better hint, think about Java. Have you seen something like this in Java or the Java virtual machine? Garbage collection. What does garbage collection do? And how frequently does garbage collection happen? JVM, right? So there might be some setting in the JVM that will tell you, well, okay, do garbage collection at this threshold or at this time interval or something of that sort. That exact same terminology is ported over to SSDs as well, right? At some point in time, so because you can't do in-place updates, at some point in time you would have a lot of invalid pages. So if you are making changes to a file, right? You're making repeated changes to a file, at some point in time you'll have a lot of invalid pages. And if you create a new file now, you can't really, because you need to erase all those blocks that contain all those invalid pages. Right? So for doing that, you need to do what is known as garbage collection, which essentially is a very known feature in things like the Java virtual machine, right? Okay, so, sorry, go ahead.
Granularity is no page. Instead of, I can't get individual bytes in a page.
You can't get individual bytes in a page. Well, I mean, you can need individual bytes in a page. So you can say, well, okay, I need these 2 bytes. But still, you would have to read the entire 4 kilobyte page.
The speed is coming from the increased granularity, like the size.
That's one part of it. Actually, that's a very good point. So where is the speed of the SSD coming from? Why is the SSD faster than a hard disk drive? All right. So put it different way, why was the hard disk drive slow? Mechanical moving parts, right? So you're getting rid of those motors and those moving things. The millisecond latency part of it is just gone, right? So now it's essentially like a memory access, right? So it's like accessing DRAM, but the device is slower, right? So memory is made up of 1 transistor, 1 capacitor. This is made up of flash, which is essentially slower. The interfaces are slower as well, but that's a different point. But the majority of the performance benefit is coming from the fact that if you know where your data is, you just do, transfer of electrons. So a part of it is because, so there are multiple things. One, the interfaces themselves are slow, right? So you have, in the case of DRAM and the CPU, they are very tightly coupled by the memory channels, right? In this case, you have to go over the I/O bridge, then you have to traverse some other bus to get to this device. Bunch of stuff happens here, then the data gets back. So that all adds up. Okay, good point.
As I understand, you have a translation table.
Uh-huh. Right. Yes, very good point. So that's what I was kind of getting into, right? So we talked about how this translation or this mapping has to be maintained, right? This mapping has to be maintained for you to actually figure out where your data really is. Where do you think that mapping would be maintained? Should it be maintained on the CPU side? Should it be maintained on the SSD itself? What would be the best place for that mapping to be present at? SSD itself, why? Exactly, right? So this is information that is local to that storage device, right? So if you have a bunch of files that are sitting at various locations in the SSD, irrespective of whether your SSD is plugged into this device or that device, you should still know where your files are sitting, right? So that mapping table is actually stored within the SSD. Now, yes?
Translation takes a lot of time.
It can, right? So it all depends on how you actually store it, which brings me to the other point. So if you look at another view of the SSD, there are multiple components that go into actually making that SSD. So we saw these NAND Flash chips, right? We saw in the last thing. There are a couple of other components within the SSD itself. So one is essentially known as the flash controller. And then there is something which is known as the host interface logic, right? So the host interface logic is responsible for interpreting what's coming from the CPU side. There's a program that's executing, and it's saying, give me that file, give me 2 bytes from that file, write to this location. Those are the commands that are coming from the CPU side. This guy is sort of responsible for interpreting that. Now, once they get to the SSD, you have to convert those commands into SSD-specific commands. The same way it was happening in the case of memory, right? So the CPU says, load something, store something. The DRAM doesn't understand loads and stores, right? It knows which row, which column, which rank, which bank to go to and read or write the data from, right? So that conversion has to happen from a load store interface to a DRAM command specific interface. That's essentially the job of this box over there, right? The flash controller is responsible for a whole bunch of different things. We will talk about some of them later on. But coming back to mappings, right? So the mappings are local to the SSD for each particular file. So essentially, they must be sitting somewhere over here along with the rest of the data, right? So the mapping is the metadata. The file that you're looking for is the actual data. Now, if your mapping was stored in the flash itself, you first have to go and look up the mapping, right? Then figure out where your data is actually located and go look the data up. How can you make that efficient? That's slow, right? And the answer is right there on this slide. Huh? Maintainer? Did I actually write that? Okay, no. All right. So, where do you maintain that cache? That's the correct answer, by the way. In the memory, exactly, right? So, anything that you want to become faster or more performant, you essentially add a layer of cache, right? I mean, that's how you typically do it in designing systems, right? So that's essentially what has happened over here as well. So there is this memory, which is essentially nothing but a couple of DRAM chips that are sitting over there, which are responsible for caching some of the translations for these, file to page mappings that you might have over there. Again, there is a whole bunch of other reasons why there is more memory there. So if you look at this flash controller, it's pretty solid ARM core, so usually a 4 or a quad core ARM SoC of sorts, right? And it's there because it's supposed to be doing a whole bunch of different things, which we'll just talk about. So think of this flash controller as something that is responsible for doing a whole bunch of bookkeeping operations within this SSD itself. The memory is sort of the memory that's associated with this ARM core, but it's also used for caching the translations that we have talked about before, right? Okay. All right, so what's the job of this flash translation layer? So what exactly is the flash translation layer? So I've been talking about the SSD does things in granularities of pages, right? But somebody has to tell the CPU side or the application side that, okay, translate this file into that particular set of pages that you have to access over there. That's essentially the job of the flash translation layer, right? So there's a layer of indirection that sits in the middle that catches all the requests that are coming from the CPU side and translates them into the requests for reading or writing to particular pages in the SSD itself, right? So the FTL, the flash translation layer, is responsible for maintaining the logical to physical address mappings. So again, this is very similar to the virtual memory stuff that you saw before, right? So the physical address mapping is the actual page on the SSD that your data is in. The logical address mapping is essentially the logical block address or something similar that comes in from the application side. We talked about how things need to be erased first, right? Who does that? So in this case, it's the FTL, right? So for example, think about a refresh operation in DRAM. Who does that? Who sends out that refresh command to DRAM? The memory controller, right? So similarly, in this case, it's the flash translation layer, which is essentially a piece of software that's running on that quad-core ARM SoC that we talked about before. And again, quad-core ARM SoC is just an example. It could potentially be something else as well, right? So it carries out those, okay, now we have run out of all the blocks that we can write to. So get me some more free blocks. Do the garbage collection, right? So that essentially is the another job of the FTL. I'm going to skip over where leveling for now. If I have the time, I'll get into that. All right. Okay. All right. So I think we have talked a little bit about garbage collection here as well. So let me just go through a quick animation which will give you a better idea as to what garbage collection is and how that actually happens. So consider this sort of a very simple example where you have a block which has 4 pages, right? So there is block 0, block 1, block 2. Each one has 4 pages, and there is some data that's written inside these pages, A1, B1, A2, B2, C1, C2, right? Now, each one of the pages that has valid information has a valid bit. The pages that are in the erase state, which essentially means that these are the places that I can actually write new data into, are valid or marked with an E. Now, let's say I have a write to A1 and A2. Can I just write something over there? Can I write into block 0, page 0, and block 0, page 2, or page 1 and page 2? Can I just do that? I can't, right? So what I need to do is essentially find 2 new pages, update the information, and write them to a new location. What I also do is I say that, okay, now these 2 pages are now invalid, all right? So I have done that. Now, let's say something kicks in, and again, this is a very trivial example, so bear with me. Something kicks in and says, I need 4 free pages now, right? There's an application that comes in, creates a new file, and that says, I need 4 new pages. How do I get 4 new pages? What I need to do is I need to sort of copy these valid pieces of data, B1 and B2, onto these free blocks or free pages over here, right? So if I do that, then these 4 pages over here in block 0 are now all invalid, which essentially means I can actually erase all the data over there, right? So if I erase all the data over there, right? So, whoa, okay. So I can now erase block 0, and essentially now I have all these 4 blocks which are essentially ready to be written in block 0, right? So this periodic sort of probing and figuring out how many blocks are left and whether we should go out and get some more free blocks is another job of the flash translation layer. All right? Sorry? Absolutely. So data movement doesn't matter when you do it, is always costly, right? The one sort of a saving grace here is that the erase operations are actually pretty slow, right? So while you are, well, in this case, you can't actually do this parallelly. But yes, the data movement is actually very costly, right? So because of this data movement, there is another problem that's happening over here. So can somebody tell me what the other problem that happened in this particular example? So we have data movement, that's always a problem, right? So in this case, so let me give you a hint. We can't do in-place updates, right? I can't take A1, change it, and write it back. Right? Because of that, there are certain problems that are sort of happening over here. Sorry? Lot of extra writes are happening. Why are the lot of extra writes happening? Right. So you're not able to do in place. That's why you have to read out the data and write it over there, right? So that is essentially the problem that is known as write amplification, right? So for example, if you had to flip a bit in a 4 kilobyte page, which essentially means you have to read a 4 kilobyte page, you have to flip a bit, and you have to write a 4 kilobyte page, right? So what typically would have been just 1 bit flip in a hard disk drive is essentially a 4 kilobyte write in a SSD. Right? And that is essentially what is known as write amplification, right? So I'm going from a 1 bit write to a 4 kilobyte write. Okay? That's well, actually a very bad idea, but that's how SSDs work, right? So that's essentially the other sort of the term that I was going to sort of touch onto. It is called write amplification. In the interest of time, I'm going to just move over this particular animation, right? Okay. All right. So we talked about this. I've been referring to this quad-core ARM, processor that does a whole bunch of things. Technically, it's known as SSD controller, right? SSD controller is nothing but a piece of logic which could potentially be a quad-core ARM controller or something similar. It handles a whole bunch of things, right? So it keeps the mapping, as we talked about before. It keeps tracks of free pages and controls garbage collection. It has to do background garbage collection every once in a while. And I'll get back to where leveling in just a bit, right? So it's a piece of logic that runs a bit of C code, right? So all of this functionality is actually implemented in very, very optimized C code that runs on what is known as the SSD controller and takes care of all these operations that we have talked about so far. All right? Okay. I think we've covered a lot of this, the differences between the multi-level cells and the single-level cells. Where leveling, right? So one of the concerns in any non-volatile memory, not just flash, is that you have this cell, right? You have this cell that stores information. All of these cells have limited write erase cycles, right? So we talked about how you can write to it, then in order to write to it again, you have to first erase it, right? So you have write, erase, and these kind of cycles are there. Each one of these cells has only a finite amount of times that you can do write erases before it goes bad, right? No such problems exists with DRAM devices or with SRAM devices, right? You can write to them as many times as you want and nothing bad is going to happen. But with flash devices or other non-volatile memory devices, phase change memory or anything else that might be there, there is this problem of things going bad, right? If you write to them too many times. So what that essentially means is that you have to spread out your writes. If you have 10,000 different places that you can write to, make sure that you write to them an equal number of times so that one piece of data is not being written to, right? So which essentially means you have to have something or some logic that makes sure that your data is placed onto these various pages in such a fashion that each one of these devices gets an equal number of writes, right? So as to not make some of these devices were faster than the others. That's essentially the phenomena that's known as wear leveling, right? So you're trying to make sure that everything happens, or every piece of data is written to the same, or every piece of the flash devices is written to the same number of times. So think about it as sort of socialism, trying to implement socialism in a flash device, right? You want to make everybody equally happy or everybody equally unhappy, all right? Okay, so I think this is where I'll stop. I was going to go into a bit of the details into how you actually go through the stack to access these devices, but maybe we can do that at a later point. There is. Professor Govind, can I take another 5-10 minutes?
Yeah, sure.
Oh, okay, all right.
Take it.
Oh, I see, okay.
Still working on it. One point, Manu, I think this is something that we discussed that we should talk at least a little bit about.
Okay.
So I think.
Okay. All right. Okay. So let me quickly. Yes. SSDs have limited life. In the strictest sense of the word, yes. Right. So if your workload, right? So if you buy an SSD and all you do is write to it, every second of every day, then you would sort of wear it out soon.
Kind of 5 or 6 years.
Something like that, right? So if you again look at the specifications of these various devices, they come in terms of how many drive writes per day it can handle, right? So you can say, well, okay, if you give it 5 drive writes per day, so essentially means you write 1 terabyte. If the capacity is 1 terabyte, you write 1 terabyte to the device every day, then it would last for 5 years. Right? Typically, we don't do that, right? If it's in a laptop, we're not writing to it that much. Usually, you write to it once and then you read from it many times, right? So these are very, very pessimistic or very, very optimistic numbers, right? So yes, technically you can, but that's not going to happen. Yes. So there are two things, right? I mean, you can think about it 2 ways. One, think about it as something that gets stuck, essentially, right? So it has to be either 1 or 0, right? Now you have changed so many times that it's stuck somewhere in the middle. It can't go one way or it can't go the other way, right? So now you have no way of verifying whether it's a 1 or a 0, right? So it's that one thing is that it gets stuck, right? The other thing is that it behaves in such a fashion that you can't interpret whether it's actually a 0 or a 1, right? So there are two different things. One, it's stuck somewhere, so it's written somewhere between a 0 or a 1. And then the second thing is that you can't actually interpret whether it's a 0 or a 1. So both of those things can happen, right? Yes. Yes. So I'll in the interest of time, let me not go into that yet, but we can talk about that offline, right? So we'll talk about that. Yes. So then you have to just pad it wisely that way, right? So rather than doing it in sets of 1 bit each, now you have to do it in sets of 3 bits each, right? So you just have to pad your information appropriately so that you can distribute it in chunks of 3 bits. There will be some? So it's the same device, right? So rather than it's a single cell. It's a single cell that's storing 3 bits, right? So essentially, let's talk offline, right? I mean, I just want to quickly cover some of this, and then I'll take some more questions. All right? Okay. So what we have talked about so far is essentially what happens at the level of the device, right? So you have traversed all the way from your application all the way to your device, and now you're accessing the data, right? Now, what I quickly want to talk about in the next 10 minutes or so is essentially how do you actually get there, right? I mean, the idea is that something's happening magically up top, which actually translates into read me that page on the SSD, right? How does that actually happen, right? So the simplified cartoonish version of the software stack is essentially what is on this slide, right? So the idea is when an application's running, all it does, it generates read that piece of data or write that piece of data, right? I mean, it doesn't know anything better than that, right? So that is essentially what is the application that's doing, right? So it says read that file, write that file, things like that. Now, those commands for reading or writing or appending to that file are actually converted into the read or write system calls that the operating system exports, right? So Manak yesterday was talking about the POSIX compliant system calls, right? So each one of these operating system exports a bunch of these functions that lets you ask the operating system to do something on the application's behalf, right? You being the application. So what I want to do is essentially I'm an application. I want to read or write or I want to do some sort of an I/O operation. I say go read that file. That call gets translated into an appropriate OS level call, right? So a read gets translated into, let's say, a read system call, right? So now that's where we have gotten to the system call interface now, right? So essentially what we are trying to sort of understand is what are the different levels of the operating system stack through which a particular I/O request has to go through before it can actually reach the device, right? So application does read or write, it gets translated into a system call interface, which essentially then there is this another abstraction that is built on top of devices, right? So you and I understand files, right? So even the applications that you write, it understands, for the most part, it understands files, right? So go read to that file, or go read from that file, go write to that file. But the device down below, or in the case of SSD, for example, right? It understands blocks, it understands pages. It doesn't understand files. So what I as an application is talking about in terms of the file abstraction has to be sort of converted into the abstraction or into a language that the device understands, right? So the file abstraction is for us. It helps us as humans sort of figure things out a little better and organize things a little better. The block level is where the device understands how things happen, right? So there has to be some sort of a conversion between these two. So it goes to this read or write goes to the file system layer over here. Now, there is this thing called the page cache, right? And again, this is an operating system construct, right? So think about caching, right? So again, it's called a page cache. This is a construct that is there to speed up I/O accesses, right? So now, let's say you have your entire DRAM, right? So up until now, what we have been talking about DRAM is something that handles stuff to and from the CPU, right? But DRAM, or the main memory, serves other functions as well. In this case, it serves as a cache for the I/O device, right? So for example, if I have a hard disk drive, if I go to the hard disk drive every time I have to make a read, then I'd have to pay the penalty of milliseconds. Now, if this is something or this is a piece of data that I'm going to access again and again, rather than having to go to the hard disk drive, I can just cache it in DRAM, right? The operating system does that independently, so transparently to the user, to the application. It caches things that it thinks are important, or pieces of data that is going to be important, that is going to be accessed by the application again and again in the DRAM, right? So once an application has made a call to read or write a piece of data, you first want to check this cache first before actually going to the device, right? So that's why there is sort of this block over here, which is essentially a piece of DRAM or a portion of DRAM that is dedicated for caching the data from different kinds of I/O devices, right? So you check that first. If you find the data there, then that's all good. You can just return all the way back, right? And you can save the round trip time of going all the way to the device, right? Now, if that doesn't happen, I should potentially not talk about this device mapper, but then you have the block layer, right? So now there is this another level of abstraction that converts your file system sort of semantics into the kind of semantics that your device understands, right? So we talked about how the devices understand blocks and pages. This is the layer in the OS that actually sort of tries and convert this file, this portion of this file translates into this block, right? Now, that kind of goes to a device driver specific to that particular device, right? So everybody's heard of device drivers, right? Okay, so what are device drivers used for? I mean, just at a high level definition. Why have device drivers at all?
Converts the language of that device.
Sorry?
Converts the commands into
Huh.
the language required by that device.
Okay.
For example, like
Okay. So why have a device driver for, I mean, every device? Why can't I just write a device driver for a hard disk drive and be done with it? Why do I have a Seagate device that has another device driver? Why do I have a Samsung device that has another device driver? I mean, everything is in hard drive. It's just connected to the same SATA port or the same SAS port. Why do I have to have everything that? The protocol is still the same, right? I mean, the interface is ID or SATA or whatever that might be. So ISA is CPU, right? So now at the level of the devices, we're talking about interfaces. Anybody else? So you somewhat have arrived there, but exactly, right? So this thing over here, right? I mean, what the operating system expects out of a device are a certain set of things, right? So what it says is, if I ask you to do this, you give me back that, right? So that is sort of like the contract between the OS and the device itself. Now, the device driver has to definitely do that, right? So it doesn't matter whether it's a Seagate device or a Samsung device. The device driver, when the OS says, give me that block, it has to give it that block, right? But the device driver can also implement a whole bunch of device-specific optimization. So a Samsung device might be doing something differently, because of which it's shaving off half a millisecond from the critical path accesses, right? And it's allowed to do that. All it has to follow is that contract between the operating system and the device itself, right? So as I said, give me that block, it gives you that block. How it does it internally is sort of also a function of the device or the device itself, right? And each vendor does things a little differently to be able to differentiate themselves from the other one, right? And that's why they might have implemented something internally which only that device's device driver is able to understand, right? So that's why you can't plug in a Seagate device and use a device driver for a Samsung device or something similar, right? So that is sort of essentially the entire flow, so to say, right? So you have the application which does reads and writes, gets translated into operating system calls, goes to the file system. There is a piece of main memory that's dedicated for caching I/O data. Then there is a block layer that does block level or converts those file system commands into block level commands. Goes to the device driver because you have things that are specific to individual devices themselves, and then eventually it goes to the device where it, reads the data, writes the data, whatever it might need to do, right? So so this is sort of like a simplified version. Whoa, okay, all right. It really wants me to finish. So I'll just quickly finish with this diagram, and it's the one thing that we saw on the last slide is a simplified version of this diagram, right? So this is essentially the software stack for the Linux operating system, and again, it's not a very recent one as well, but it was something that would fit on this slide, so I chose this one. So this is essentially probably from 5 or 6 years back, and now if you look at the current day, which is the 4 point something kernels, the storage stack, it's even deeper, right? So when I was talking about that, accessing a device has other issues that you have to get over before you can actually get the data that you want. This is the stack that I was talking about, right? So your application sits over here, your device sits over here. Now, to get from here to here, you have to pretty much cross all of these boundaries, right? I mean, again, I'm simplifying a bit, but you sort of get the idea, right? So each one of these layers over here adds a certain latency to your overall request, right? So when you are trying to optimize accesses to a particular device, you not only have to optimize the devices themselves, but you also have to go back and look how does that affect what are, where time is being spent in all of these different layers, right? And that's why, just this entire domain of looking at storage devices and trying to optimize that not only requires you to understand, how devices themselves work, but also how do you access those devices through this entire software stack, right? Okay, think this is it. I'll stop here or no. I'll take a couple of questions and then we can talk offline. Yes?
So the pen drive also uses flash memory.
Yes,
SSDs also use flash memory.
absolutely.
The same technology.
It is almost the same technology. Okay, so
Difference only in the size or
that's a good question, right? So I'm going to throw this question back to you guys. What's the difference between a USB and an SSD? The first thing that might come to your mind, except for the size. So file system wise, okay. So let's forget the file system wise as of now. The interface, right? So the first thing that's different is the interface. Your thumb drive essentially goes over a USB, right? And SSD is usually over something which is SATA or SAS or IDE. You have USB compatible SSDs as well today, right? But what could potentially be the drawback of a USB compatible SSD as compared to something that goes in the place of your hard disk drive? Exactly, right? So USB is a pretty bandwidth limited interface, right? The rest of the interfaces have much higher bandwidth. So USB, I don't want to quote incorrect numbers, but potentially could be an order of magnitude difference between if you take that exact same device, plug it behind a USB interface, and you take the device and plug it behind a SATA or a SAS interface, right? So the interfaces themselves have much higher bandwidth allocations. So it's not the device, it's the interface that matters in that case. Good question. All right, what else? Most of these things are there. So as long as you have flash, right? As long as your backend storage is flash, all of these things have to be there. It's just that thumb drives are relatively inexpensive, so it might not be as sort of complicated as it might be in consumer grade or enterprise grade SSDs. Sometimes it might not even be there depending on what is there. But the basic requirement, which is essentially converting logical block addresses to physical block addresses, that definitely has to be there, right? Yeah, good question. Yes?
The SSD technology is now being used as hard disk caches, right?
So actually you have taken me to a slide that I had there, which is essentially, since we are here, I'm going to just do this, right? So you are absolutely right. That is also being done, right? So if you go back to my original slide where we have this timing pyramid, right, where your SSDs are potentially an order of magnitude faster than your HDDs, but they are also an order of magnitude expensive. For example, right now, if you want to create a system where you want to have the larger capacity benefit of hard disk drives, but the latency benefit of SSDs, how do you architect that, right? So essentially, there are a whole bunch of ways, and the design principles behind them are pretty similar to what we have been talking about before as well, right? You have this faster device caching data from a slower device, right? So this is, again, think of this as your L3 cache, think of this as your main memory, right? So most recently accessed data is stored, in this case, in your SSD, and whatever you don't find in SSD, you can find over in the hard disk drive. Things like that. So again, that's one example. Sorry, I'll just go with Frank over there. Yeah.
SSD as a cache, I know it's being used.
Sure.
Its endurance is less compared to the hard disk drive.
Uh-huh.
So they involve lots of reads and writes. Lots of data.
Yes. So that's a good point, right? I mean, so again, when you when you think of caches, right? So caches are usually, write once and read many times, right? I mean, that's typically what you'd expect of a cache. You bring in the data once and then you want to read it again and again unless you have to absolutely throw it out, right? So when you use an SSD as a cache, the number of writes that you're doing to it are hopefully not as frequent so as to wear it out really soon, right? It's probably not going to affect it that much. But again, that doesn't mean that wear livability just goes, or the devices become, they last forever, right? So the wear livability still has to be taken care of. Yes. So yes, flash devices have much stronger error correction as compared to DRAM devices, right? So again, I don't want to quote incorrect numbers, but there is very strong ECC that's built into each one of these flash devices. That's a good point. Yes, absolutely, because you never know, right? I mean, you could potentially, even after all those wear levelings, you could write to a cell whose data actually just fails, right? So you still need very strong error correcting codes to be present so that you can actually not, or you don't lose any data, right? Very good point. Yes.
So in the context of doing research,
Uh-huh.
especially like working like device driver,
Uh-huh.
say like controllers and all.
Uh-huh.
So is there any suggestion of tools? What kind of tools people are doing research on this?
So for device drivers, the best,
Be say for modeling this, maybe directly in the hardware, or we have to abstract it to the kind of simulator or something like that. I don't know.
right. So there are, again, simulation is definitely one methodology that you can follow anytime you want to model things like this, right? There are also emulation tools, right? So for example, you can, so again, I might be out of scope here, but there are tools which let you convert pieces of your main memory, your DRAM, in that resembles a solid state device, right? So you can think about, you carve out a piece of your main memory and say now it's a block device with a specific latency, right? So there are tools that I think RAM disk is something that would allow you to carve out a piece of your DRAM, your main memory, as a block device, and then you can do operations on it. You can create file systems on top of it, and then you can do I/O operations. So emulators are a better way to go because they let you do things with the entire software stack in place, right? And I think Deba over there works on things like that. So if you have more interest, I think you should go talk to him right after this. Any more questions? All right. Thank you very much.